Welcome to the AP discussion on nuclear physics. In this video, we're going to just do some basic nuclear physics introduction topics. Let's start with the term strong nuclear force. The strong nuclear force, the strongest force in the universe, binds neutrons and protons together in the nucleus. In order to have a good grasp and understanding in nuclear physics, you have to know some basic chemistry terms. So with each of these terms, if you don't already know what they are, make sure that you write down a brief little description for each one as you go. To help with our discussion, I'm going to use the helium atom. And the helium atom has an atomic number of 2 and a mass number of 4. Okay? So in our first term, nucleons. Nucleons is any particle in the nucleus. So nucleons is the combination of both protons and neutrons that exist in the nucleus. And what we see by looking at the helium nucleus is that there would be 4 nucleons. That's what the mass number tells us, is the number of protons and neutrons in the nucleus. So 4 would be the number of nucleons in the helium nucleus. Atomic number is simply the number of protons in the nucleus. That's the bottom number in the atomic symbol over here. And that atomic number in this case is 2, and what that tells us is that helium has 2 protons. Okay. The mass number, which we just discussed, is the top number, and that top number for the helium nucleus is 4. Okay. So again, the mass number tells us the number of protons and neutrons in the nucleus. An isotope are variations of a particular element in which you have the same number of protons you have to in order to be that element, but you have a different number of neutrons. So for example, an isotope of helium would be helium-2 and a mass number of 5. And of course, what that shows is that it had 2 protons and 3 neutrons, making it an isotope of helium. All right, next we're going to take a look at some nuclear reactions. And the first thing we're going to take a look at here is nuclear fission. And what you need to be able to do is recognize a reaction for nuclear fission. And in this reaction we have uranium-235 that is hit by a neutron, and typical nuclear fission reaction here. And that breaks down into barium-142, krypton-91, and 3 additional neutrons. Well, in fission, what those 3 additional neutrons do is they then go and each split their own uranium-235, and you get from this what is called a chain reaction. You can quickly see how you go from 1 reaction to 3, which would go to 9 to 27, etc., etc. So you get this great exponential growth in the nuclear fission reaction. In addition, you get a tremendous amount of energy given off in that process. And we'll talk more about that energy in comparison to its energy produced in fusion here in a moment. But you recognize this as a fission reaction because you have something large, and fission means to split. So you have this large atomic nucleus that gets split into smaller atomic nuclei. Nuclear fusion, on the other hand, we have small elements that are combining together to produce larger elements. In this case, we have 2 helium isotopes that are combining together to form natural helium, and then we get natural hydrogen, 2 atoms of natural hydrogen also produced at the same time. This is one of several nuclear fusion steps here, just showing one as an example. In the process of doing this, we also get a tremendous amount of energy given off. And the first thing we want to talk about here is that how do you recognize this as a fusion reaction? And you recognize that fusion means to combine, fuse, put together. And so we have light elements combining into larger ones for fusion. The other thing that we want to talk about here is a comparison. If we're comparing one fission reaction to one fusion reaction, then the energy produced by the single fission reaction is greater than the energy produced by one fusion reaction. However, if you measure pound for pound, so to speak, mass for mass, you would get much, much greater energy from a fusion in, say, 1 kilogram of a fusion reaction as compared to 1 kilogram in a fission reaction. Next, we're going to talk about that you need to know your nuclear particles. So we're going to list each one of these here, and we're going to draw what each one looks like, the symbol that's used for each of these. The first one is, and we'll go through the 3 radioactive decay particles, and they were discovered in this order, and therefore given these names according to the Greek alphabet. Alpha, beta, and gamma are the first 3 letters of the Greek alphabet. So the first one you have to know is the alpha particle. The alpha particle is a helium nucleus. So the symbol for the alpha particle is helium with a mass number of 4 and an atomic number of 2. Since it's a helium nucleus, the other thing that you need to keep in mind is that the alpha particle has a positive charge. The next discovered particle was the beta particle. The beta particle is a high-speed electron. So the symbol for that is E, has an atomic number of -1 because it's an electron, so -1 meaning negative proton. And since there are no neutrons or protons, it has a mass number of 0. Because it's a high-speed electron, the thing to keep in mind here as well is that a beta particle has a negative charge. Next is the gamma particle, which is a photon, and the symbol, as indicated here, is the Greek letter lowercase gamma, and because it doesn't have any protons or neutrons or electrons, it's a photon, it has no mass, it has atomic number of 0 and a mass number of 0, and it has no charge, it's neutral. A proton. What element could we use to represent a proton? Well, that would be a hydrogen nucleus, because hydrogen has an atomic number of 1 and it has no neutrons, so it has a mass number of 1. So there's your proton, and of course it has a positive charge. A neutron, we just use the symbol lowercase n, has no protons, of course, so it has an atomic number of 0, and it has 1 neutron, so it has a mass number of 1. Would also be helpful if you knew what a deuteron and a tritium atom were, and these are both isotopes of hydrogen. Deut is the prefix that means 2, so this would be a hydrogen isotope with a mass number of 2, and of course with tritium you see tri, and that is a mass number of 3, so that is a hydrogen isotope that has 2 neutrons and 1 proton. Lastly, in our little introduction here, we're going to discuss that you must be able to balance nuclear equations. And before you freak out if you've taken chemistry, okay, this is much, much easier than balancing equations in chemistry. Before we do this, and we're going to use number 17 in the problem set as our example here, so I'd encourage you to take that out and be looking at that and write these down as we go. We need to talk about the difference between natural transmutation and artificial transmutation. The 3 examples that you see here in number 17 are natural transmutations. What does that mean? That means an element naturally decays into another element and also gives off a radioactive decay particle when doing that. And an artificial transmutation, such as the ones pictured in number 19 on the problem set, you actually are taking an element, bombarding it with some kind of nuclear particle in order to make it become some other element. And that would be an artificial transmutation because it's a man-made. In other words, man is bombarding an element in order to make other elements. Okay? All right, so let's take a look at this. This is really simple. The only rule of thumb that you need to follow with this is that the mass numbers and the atomic numbers always have to add up and be the same on each side of the equation. So when we take a look at A, for example, we have boron 12 decays into some question mark, some other element, plus it looks like a beta particle is given to us here. So if we take a look at this, we've got boron 12 decays into, and what's a beta particle? Let's draw that again. We've got an E, has a mass number of 0 and an atomic number of -1. So what was the element that boron 12 decayed into? What number plus -1 equals 5? Well, that would be an atomic number of 6. What number plus 0 equals 12? And of course that would be 12. Well, then we look at our periodic table of elements, which you're not required to memorize, but some of these you just learn to know over time. And the element with the atomic number of 6, of course, is carbon. So boron 12 decays into carbon 12 plus a beta particle. In B, we have what I believe is thorium 234 decaying into radium 230, and what they're asking in this question is, what is the natural decay particle given off from doing that? So let's start by rewriting here. 234, 90, or TH, decays to radium 230 and 88. Well, all right, we'll get rid of that. Write the 88. And radium plus, all right, so 230 plus what equals 234? So our mass number has to be 4. And 88 plus what equals 90? Our atomic number has to be 2. So what do we recognize that as? Well, that has the mass number and atomic number of an alpha particle. What you need to also recognize here is that's an alpha particle and it's not natural helium because it's a natural transmutation, so it has to be the radioactive decay particle there. In our last question, we have something unknown that decayed into nitrogen 14 plus a beta particle. So let's start with our right side, rewriting that. We've got 14,7, and that's nitrogen, plus, and our beta particle would be 0, -1. So 7 plus -1 gives us an atomic number of 6, and we already know what that element is. And 14 plus 0 gives us a mass number of 14. Okay, so we know that that's carbon by the fact that it has an atomic number of 6. So this is an isotope of carbon. Carbon 14 decays naturally into nitrogen 14 plus a beta particle. All right, we're going to stop there and encourage you to come back for another lesson in nuclear physics, which will be on binding energy. More to come.